Aya, with Morgan and Aya graded bonus quiz 2. She's not here yet. I don't know why not, but presumably she has these graded. So, if she doesn't make it today, if that's the case, I don't know why. See her tomorrow in discussion class, and you can get back your bonus quiz if you don't get it back today. Keys posted. Now, we take a look at one final consideration at the tail end of chapter 23. It's another metallurgical consideration, which has to do in this case with the chemical method by which nickel metal is purified. But, as we shall see, the principal purpose of discussing this, the Mohn process, about the purification of nickel, is that it provides an excellent springboard into chapter 24 on transition metal coordination chemistry, which I purposely put off till the tail end of our chemistry considerations for 2046, because, as we have already commented, transition metal chemistry is in many ways a lot more detailed, a lot more sophisticated, a lot more interesting than the chemistry of non-transition metals. Why? Because non-transition metals in the main have a fixed set, a fixed number of valence electrons. When 1A metals react, they lose 1 electron per atom. That's it. 2A metals react, they lose 2 electrons per atom. That's it. Aluminum reacts, it loses 3 electrons per atom. That's it. Those are the principal A family metals. But transition metals can, under appropriate circumstances, develop a number of different stable oxidation states. So they have a variation in the number of valence electrons which they have. The number of valence electrons which participate in the chemistry of the atom depends upon the chemical environment in which the atom is placed. So now we begin to take a look at the chemistry of these transition metals in detail, and see how, for the first row transition metals, the 4s electrons behave, given that the 4s electrons are valence, and in certain cases the 3d electrons behave. Because the 3d electrons which the first row transition metals have are also valence. Keep in mind, though, transition metals really stop with the copper family. Even though zinc, cadmium, and mercury is a short vertical column, the zinc family of elements do not show chemistry which would qualify them as transition metals. Because under no circumstances do these elements, zinc, cadmium, and mercury, ever do anything with valence d electrons. Point to d electrons which they have are in fact not valence. They don't participate in their chemistry. But back to this. Nickel, obtained by metallurgical processes, obtained from nickel-containing ore, probably nickel oxide or nickel sulfide, and then prepared from the ore by reduction. In this process, it's generally the case that the nickel which is obtained by reduction of the nickel-containing ore will also contain cobalt, because the original ore will also contain oxidized forms of cobalt. You shouldn't be too surprised to find that cobalt and nickel show a lot of similarities in their chemistry, since they're neighboring atoms of period number 4. The nickel sample, in this case contaminated with cobalt, is treated with a vapor of carbon monoxide at a fairly low temperature, lower than the boiling point temperature of water, 60 to 80 degrees centigrade. And at this low temperature, Carbon monoxide molecules do not react with cobalt. I've written here a note. I've seen students in the laboratory when, for example, in assignment number 2, 46L, when you're asked to do some precipitation investigations with potassium ion and ammonium ion and their ability to react with cobalty nitrite complex ion. Students have a habit of writing the formula for cobalty nitrite complex ion with capital C, capital O. And when I've seen this, I just exit off and send the student away. They don't know what's going on. That's what's going on. Cobalt and carbon monoxide are quite different. Damn it. One's an element, one's a compound, if nothing else. You can write this as representing this or this as representing this all you want. It won't make them equivalent. Just like you can say Na plus is the formula for elemental sodium. That will not make it true. Back to the chemistry. So what this reaction achieves is separation of the nickel from the cobalt. The nickel reacts, the cobalt doesn't react, the nickel compound is gas phase, and cobalt is solid, doesn't react. So the separation has been achieved. Then when we take this gas phase compound, heat it up to about 200 degrees, it decomposes, and we get pure nickel. So this shows us how, from the chemistry of metallurgy applied to nickel, we get pure nickel. But now we get to the fun stuff. Stuff which springboards us into chapter 24. First, let's take a look at this reaction. Can we categorize it? Is it a redox reaction or is it Lewis acid, Lewis base? There's the reaction equation. Let me operate on this formula before we proceed. To show you that this material, as are all compounds, is in total zero oxidation state. What do you think? How many vote Lewis acid, Lewis base? How many vote redox? And 2,000 points off for everybody who didn't vote. So when you look at the grade book tomorrow, for those who didn't vote, you'll see a new column added. Non-voters minus 2,000. Then you can all say, ah! And then next time you'll vote. Now then, if this reaction is redox, then we would well expect nickel, if this is a redox reaction, we would expect nickel to be oxidized or reduced. This is a metal, this is a non-metallic molecule. Would you expect nickel to be oxidized or reduced? Oxidized. Oxidized. Have you not found so far that when metals react with non-metals, if it's a redox reaction, which until now has always been a redox reaction, the nickel gets oxidized, the metal gets oxidized, and the non-metal gets reduced. The metal develops a positive oxidation state, the non-metal develops a negative oxidation state. So if this is redox, this would be an ionic compound. What do you know about ionic compounds under normal laboratory conditions? What kind of properties do they exhibit?
Solids.
What is that?
Solid.
Solids. Not just solid, but distinctly crystalline. Crystalline solids. This stuff is a gas. And this is only at a temperature of 60 to 80 degrees, not even up to the boiling point temperature of water. You think that's ionic? No. So what's happening here is a Lewis acid, Lewis base interaction of nickel atoms reacting in what capacity? Lewis acid or Lewis base? all complex compound or complex ion formation reactions, which is entirely what we're doing in chapter 24. They're all Lewis acid, Lewis base. Remember what Lewis acid, Lewis base interactions are? Lewis acid is the partner in the reaction which supplies one or more empty valence orbitals. The Lewis base supplies non-bonding pairs to make, by taking occupation in the empty valence orbitals of the Lewis acid partner in the reaction, to make coordinate covalent bonds. That again is what we talked about at the end of chapter 19 and what I recall reviewing on the board not too long ago. Does nickel atom have empty valence orbitals? Well, clearly if nickel is the Lewis acid in this reaction, it's got empty valence orbitals. What will you do to identify the empty valence orbitals which nickel atom has?
Lewis structure.
Lewis structure won't help you much. Lewis structures for atoms are rather meaningless.
Or electron.
Electron configuration. 28 nickel. Argon. Four S2, 3D, how many? How many electrons does this represent? 18. Well then, 3D, how many?
8.
Statement. In our considerations of transition metal chemistry, you will regularly have to identify oxidation states of transition metal atoms in compounds or complex ions which contain these transition metal atoms. So how will you get at these oxidation states? You're going to have to start with the valence electron configuration for the atom in question. So if you do not remember how to get at transition metal atom valence electron configurations, say for the first row atoms, keep in mind chromium, exception to the Aufbau rule. 3D5 4S1 rather than 3D4 4S2, and copper the next exception. 3D10 4S1 rather than Aufbau predicted 3D9 4S2. So I think it's convenient. You've got your mind focused on the two exceptions. Pick iron. Pick iron because it's rather in the middle of this first row of transition elements. Atomic number 26. So you start by recognizing that elemental iron is argon, 3D6 4S2. And you know on ionization, the highest n value electrons always go away first. On developing one of the common oxidation states shown by iron, positive oxidation states. What are the positive oxidation states shown by iron? You know this. Let's put it to use. Common oxidation states shown by iron. There are only two. +2 and +3. So iron +2 is 3D6 4S0, and iron +3 is 3D5 4S0. Where iron +3 has got this half-filled large capacity 3D sublevel, arguably stable on the basis of being a half-filled large capacity sublevel. And if I ask you to get at oxidation states for atoms, transition metal atoms, which are not in that first row, I'll have to give you some information which will allow you to do that. Because you may recall, we pointed out that in the nickel family, given that we're talking now about nickel, palladium, and platinum, they're all in the same family, and no two of these elements have the same valence electron configuration. Interesting. They have the same total number of valence electrons, 10, but they don't have the same valence electron configuration. Well then, you can look at this at a glance and see the only remaining possibilities are 3d9 4s1 and 3d10 4s0. There's only other possibilities if you still got the 10 valence electrons. And by looking at the electron configuration table that's in chapter 23, earlier on in chapter 23, you'll find that palladium, if my memory's right, is 3d10, is 4d10, 5s0, and platinum, interestingly enough, is 5d9, 4s1. And you may well ask why. I have no idea why. I don't know that anybody does. But that's its configuration. In any case, Lewis acid-Lewis base reaction. I asked the question, how many empty valence orbitals does a nickel atom have? Tell me. How'd you get that?
You have your s orbitals plus your d orbitals and divide by 2. Well, the amount filled.
I don't know where you got this mysterious recipe, adding orbitals dividing by 2.
Well, adding electrons, like complete orbital of d and s.
Wait a minute. Here, diagrammatic representation for the 3AD8 configuration. Here's a diagrammatic representation of the 4s configuration for an atom of nickel. All right? Well, once we're in energy level number 4, because nickel is from period number 4, we have an energy level with an electron capacity of how many? You remember the simple quantum mechanical recipe to get total electron capacity for an energy level? Don't remember? Energy level identified by principal quantum number n. Two n squared. What n are we talking about for nickel? 4. Well, here comes the hard part. 4 times 4, 16, times 2, 32. So how many orbitals in energy level number 4? Because in any orbital, we can put how many electrons? 2. So 32 divided by 2 gives us 16 orbitals. I've shown here for nickel, 1, 2, 3, 4, 5, 6 orbitals occupied. So there's a whole bunch of orbitals still there. They're all part of the valence environment and they're all empty. What are these other orbitals which are part and parcel of energy level number 4? Well, after 4s, what do we encounter? 4p. That's a package of how many orbitals? 3. And then 4d. That's a package of how many orbitals? 5. And then, finally and at long last, we come to f orbitals. And an f sublevel is a package of how many orbitals? 7. You count them all up, and you'll get 16 for energy level number 4. In any case, we've demonstrated that nickel has got a whole bunch of empty valence orbitals. Forget the 4f. But definitely include 4p and 4d. Well, that gives us 8 empty orbitals. Plenty of them. Now then, what about carbon monoxide? because carbon monoxide for this reaction has been recognized to be a Lewis base. That means it's going to supply an electron pair from its valence environment, which will become a bonding pair, as a coordinate covalent bond is formed between between nickel and carbon monoxide. So, when we talked about Lewis bases, we said the simplest, best way to recognize the ability of a species to be a Lewis base is to do what for the species? What? Look at your neighbor's paper. Ask the teacher. Go to tutoring zone. What's the best way? Write a Lewis structure. Because in the main, the valence electrons from the Lewis base, which are used to make coordinate covalent bond interactions, are non-bonding pairs, which of course on bond formation interaction become bonding pairs. Well, here's carbon monoxide. 1, 2 non-bonding pairs. An interesting species from a Lewis structure analysis standpoint, because this has a negative formal charge on carbon and a positive formal charge on oxygen, which is contrary to the way we'd like to have these formal charges positioned based on atomic electronegativity. Oxygen being much more electronegative than carbon. But this is the only Lewis structure you can write for carbon monoxide, given that studies demand the recognition of this very strong bond interaction between carbon and oxygen in this molecule. This is the second strongest bond known in the world of chemistry. The second strongest covalent bond interaction known in the world of chemistry. Number 3 is the triple bond for the nitrogen molecule, and we'll talk about number 1 shortly. Okay? Also, in learning to write Lewis structures, you are asked to recognize that this so-called octet rule applies to even electron species. What's that mean? Total number of valence electrons for the species is an even number, no more, no less. Well, 4 valence electrons from carbon, 6 valence electrons from oxygen, that's 10. That's an even number. So this is an even electron species. And it contains carbon and oxygen. Because the octet rule also goes on to tell us, when I find carbon and or nitrogen and or oxygen, that's it. Carbon and or nitrogen and or oxygen in an even electron species. These atoms are exclusively, no exceptions known, octets. How about that? Well, that helps us a lot when we're going to sit down and write Lewis pictures for a whole bushel basket of molecules which contain carbon as the principal skeletal atom, doesn't it? Like organic molecules. Last count I saw is over 10 million of these things now known. And chemists are making more, discovering more by natural material analysis every day. 10 million, over 10 million now known. 5 years from now, probably be 15 million. Who knows? So, you're going to write a Lewis picture for an even electron species. You've got carbon and or nitrogen and or oxygen in its composition. These atoms got to be octets, period. Hey, that gives you a lot of assistance in trying to develop the overall Lewis picture. Here it is. There's no other possibility where each atom can be so-called octet. 8, 8. Triple bond. Question. Based on what we have on the board, can you decide when carbon monoxide behaves as a Lewis base, does it use this non-bonding pair only? Does it use this non-bonding pair only, or on occasion it uses this non-bonding pair, on other occasions it uses this non-bonding pair. So three possibilities exist. Carbon monoxide behaving as a Lewis base uses exclusively the carbon atom non-bonding pair, exclusively the oxygen atom non-bonding pair, or depending upon the environment, one or the other. Those are three possibilities. How do you vote? Non-vote this time costs you $10,000. Don't even show up for the rest of the exams. You can't possibly pay the bill. Carbon atom non-bonding pair only. How many vote for that? What determines the ability of an atom to be a donor atom if in its valence environment it has a non-bonding pair?
Great negative charge in its electron cloud.
Great negative charge in its electron cloud. This is a molecule. There's no negative charge in the electron cloud.
It's hybrid orbital.
Hybrid orbital. Both of these atoms are how hybridized?
SP.
SP. Any other? Properties of an atom when it's in a molecule, which relate to its ability to be a donor atom, to make a coordinate covalent bond, behave as a Lewis base. How about that? Electronegativity. Oxygen is much more electronegative than carbon. On that basis and that basis alone, which atom should be the better electron pair donor?
Oxygen.
Well, I heard two votes. I heard oxygen and carbon. Both answers can't be right. Remember what this electronegativity property does? It stabilizes valence electron density. We're talking about the ability of an atom, because it's got a non-bonding pair in its valence environment, to use this as a reactive non-bonding pair. It's going to make a bond with something else. This is the atom of greater electronegativity or of lower electronegativity with a non-bonding pair. Which one's more reactive? Lower electronegativity. That points to carbon, doesn't it? Now then, on the board, we also have supplied you with formal charge analysis for this molecule. The formal charge analysis shows negative formal charge on carbon. Well, would you expect non-bonding electron density to be better shared by an atom with negative formal charge or by an atom with positive formal charge? You want to try to get electron density from something which is positive in any way? That's not easy to do. But Coulomb says from something that's negative, okay. So guess what? Donor end of carbon monoxide is this electron pair and only. Carbon monoxide shows no examples of using the non-bonding pair from oxygen to make a coordinate covalent bond, which is one reason why the formula for nickel tetracarbonyl, the name shouldn't surprise you, nickel tetracarbonyl, that's carbon monoxide named as a ligand. Ligand, what the hell is this word? Ligand. Equal TM chemist name for an LB. What's LB? Lewis base. Yeah. Now you can look it up in history books, find out why they call them ligands. I don't care about that. It's just part of the language. Okay. Now we looked at the ability of carbon monoxide to be a Lewis base. Next question. When I make this sigma coordinate covalent bond, in this case from carbon monoxide to nickel, do you think the sigma coordinate covalent bond will be particularly strong? Did you recognize when we talked about Bronsted-Lowry acids, boy, we've talked a whole lot about Bronsted-Lowry acids this term, haven't we? That each and every Bronsted-Lowry acid-base reaction is also Lewis acid, Lewis base. Because when a Bronsted base makes a bond with H+, it always does so by converting a non-bonding pair to a bonding pair. So what investigation might you do? What experiment might you conduct to find out which of these molecules? This is ammonia. This is carbon monoxide. We've just offered arguments to indicate why when carbon monoxide behaves as a Lewis base, this non-bonding pair is the one that's used. When ammonia behaves as a Lewis base, clearly it's got to be this non-bonding pair. It's the only one it's got. If I take 1 molar hydrochloric acid solution and bubble in ammonia gas, and also bubble in carbon monoxide gas, if I've got a liter of this, I got a mole of available H pluses, because I got a mole of hydronium ions. So I'll bubble in a mole of this, and I'll bubble in a mole of this. What do you think is going to capture most of the H pluses? Or maybe even all of the H pluses? Or do you think the H pluses will wind up being rather uniformly divided between this gets about half of them and this will get about half of them? I made a mixture of a mole of hydronium ion with a mole of this and a mole of this. Because what we're doing is to think about an experiment which will measure the ability of carbon monoxide to behave as a Lewis base, the strength of its ability to behave as a Lewis base, okay? Any idea? You find carbon monoxide listed in our acid base table. Didn't find it there. Now then, of course, carbon has a lower electronegativity than nitrogen. That would support the conclusion that this would better grab H plus than this. But let's not stop our considerations at this one atom consideration. Do these atoms inhibit the ability of nitrogen to use this non-bonding pair? Does this atom inhibit the ability of carbon to use this non-bonding pair? Hydrogen atoms inhibit this non-bonding pair usage? This oxygen atom inhibit this non-bonding pair usage? Remember this? If we do the experiment I just described, you won't find any of the H pluses winding up with this thing. Which will show you this is a much better Bronsted base, and in this case, Lewis base, at least toward H plus, than carbon monoxide. Okay? The point of this is to recognize that carbon monoxide, even though we've talked now about its ability to behave as a Lewis base, given that this reaction goes, is not a particularly effective Lewis base as a consequence of using this non-bonding pair to make a coordinate covalent bond interaction. Keep your mind on that one as we proceed. Now let's talk about question 63. Nickel tetracarbonyl is diamagnetic. What's that tell us? Does it tell us anything important? Does it tell us anything about unusual bonding in this molecule? Does it tell us anything about why this molecule is stable? Here's the nickel atom. Remember we wrote its electron configuration not too long ago? When I make nickel tetracarbonyl, I take it to the laboratory and I do some property investigations on it and find out it's diamagnetic. Is elemental nickel diamagnetic? Is elemental nickel diamagnetic? Is elemental nickel diamagnetic? Or is elemental nickel paramagnetic? Elemental nickel's got two half-filled orbitals here. Two unpaired electrons. This thing is paramagnetic. You'll learn this in 2045. Any species which has in its valence environment one or more half-filled orbitals, one or more unpaired electrons, is paramagnetic. Nickel is paramagnetic. Per atom, you've got two half-filled d orbitals, two unpaired electrons. This stuff is diamagnetic. So something's got to happen to this configuration when nickel makes bonds with carbon monoxide, because the paramagnetic character disappears. What's got to happen to this configuration? Well, how must this configuration get rearranged if this converts to a diamagnetic configuration?
Force to those electrons drop down to 3d10, and then the other...
They drop down to the 3D sublevel and give you a 3D10 config.
Yeah.
Okay? So here we go. The 3D config for the nickel atom in nickel tetracarbonyl. It's got to be this. If it was anything but this, the damn thing would be paramagnetic. But it lost its diamagnetic character. It's lost its paramagnetic character, the nickel atom, when it made bonds with carbon monoxide molecules. So this configuration, right here, how to become that configuration? And the only way that could happen is if this 4s electron pair, like magic, jumped back to 3D to wind up with this configuration. Now, at this very instant, by converting this configuration to this configuration, the 4s valence orbital is now empty. And the 4p valence orbital, valence sublevel, was always empty. Tell me, to make this stuff, how many coordinate covalent bonds do we have to make? 4. And each is made by carbon monoxide using a non-bonding pair from carbon to occupy an empty valence orbital on nickel, the atom with which the 4 carbon monoxide molecules are reacting. Which orbitals are going to get occupied?
The 4s and 4p.
We need 4 of them. And in terms of relative energy, because this is really an energy diagram, you looked at diagrams like this all the time in 2045. Now I want you to put this stuff to use. Make it meaningful. So I'll purposely exaggerate the size of the non-bonding pairs from carbon monoxide molecules which become bonding pairs. Electrons aren't different from other electrons, but I'm trying to get you to realize which of these electron pairs were supplied by the carbon monoxide molecules when they reacted with nickel. So tell me. How is nickel hybridized in nickel tetracarbonyl? You remember how you determine hybridization?
sp3.
You look at the orbitals involved. 4s and 4p, all of them. So from this simple game, we've been able to predict the hybridization exhibited by nickel in nickel tetracarbonyl. Tell me, what geometry do you associate with this sp3 hybridization? Tetrahedral. So in order to confirm this, we'll go to the laboratory with a sample of nickel tetracarbonyl and do a structure determination on it. And guess what we find out? It's tetrahedral. How about that? We already recognized by measurement it's diamagnetic, and now it's tetrahedral. How about that? All follows from stuff we've already talked about. So take note. Carbon monoxide, as a sigma donor, has shown itself not to be particularly strong. Couldn't even compete with ammonia when it came to H plus gathering. But now we're talking about a reaction with nickel metal. Nickel metal plus ammonia is strictly no reaction. I don't care what conditions you establish, you won't get ammonia to react with nickel metal. But we got, hey, nickel and carbon monoxide are reacting, and not at particularly unusual or stringent conditions. So we're seeing that the ability of a species, in this case nickel atom, to behave like a Lewis acid depends very much on the Lewis base with which the Lewis acid reacts, and vice versa. The ability of carbon monoxide to behave as a Lewis base depends on the Lewis acid with which it reacts. That's just the name of the game. Like way back to chapter 18 when we started talking about Ka values. We said, hey, you got to recognize the Ka value is measuring the ability of a Bronsted acid to protonate water. Because as soon as you change the stuff that's being protonated, you change the value for Ka. Along with that, we said, what if we dissolved a bunch of acids in ammonia as solvent? Hey, these Ka values all go up big time. Because ammonia is a heck of a lot better H plus grabber than water. And now, the other day, we said, hey, if I dissolve a bunch of acids in something like ethanol, I'm going to see all these Ka values come down. It's all stuff. You can't say, this thing is absolutely a strong acid or a strong base. It all depends on what it's reacting with. Okay? Now then, isn't it interesting that nickel reacts with carbon monoxide to make a stable stuff in which the nickel oxidation state of 0 has been preserved, which I'm sure is the first example you've ever seen of a compound containing a metal element with non-metal elements. Metal element with non-metal elements, where the non-metal element is not in a positive oxidation state. Interesting, isn't it? So we're seeing that this transition metal coordination chemistry, because that's what we're talking about here, can do some pretty interesting stuff. You think, for example, hemoglobin's important? That important? How about chlorophyll? That important?
Yeah.
That's all transition metal chemistry. You're damn right it's important. You know it's important. And now we're laying foundation for getting a hold on understanding that kind of stuff. It's different chemistry from any of the kind of chemistry we've talked about so far. In many cases, much different. Now let's talk one more thing about bond strength. Carbon monoxide shows itself, based on this investigation, to be not a strong sigma donor. Let's talk about one more investigation. Let's take a solution that contains nickel plus 2. Because plus 2 oxidation state is the most common oxidation state shown by nickel. nickel chloride, nickel sulfate, those are all +2 oxidation state compounds of nickel. Okay? We said here, nickel 0 plus ammonia, no reaction. We've already recognized that nickel 0 plus carbon monoxide reaction. So let's try nickel +2. With ammonia and nickel +2 with carbon monoxide. We're trying to get a better handle on the sigma bond forming ability of carbon monoxide. I want to understand that better. This has already dictated that carbon monoxide is not a particularly good sigma donor when H plus is the Lewis acid. But we found out that carbon monoxide makes a stable coordinate covalent bond with nickel 0. Well, let's put some carbon monoxide with nickel +2. Will this be a stronger Lewis acid from a non-bonding pair acceptor standpoint than nickel 0? Tell me. Here's a non-bonding pair. Here's nickel 0. We already know that reacts with this non-bonding pair because it makes this nickel tetracarbonyl stuff. Here's nickel +2. Which one of these do you expect to have the stronger tendency to react with this non-bonding pair? Isn't this plus? Doesn't this exert a natural electric attraction for non-bonding electron density? Much more so than this. Ain't that right, Coulomb? Something plus ought to attract electron pairs more strongly than something that's 0 charge. Right? Plus attracts minus. Well, guess what? No matter how we try, we can't get nickel +2 to react with carbon monoxide. Nickel 0 reacts with carbon monoxide, but not nickel +2. What the hell is going on here? And nickel 0 won't react with ammonia, but it reacts with carbon monoxide. Whereas nickel +2 readily makes this stuff, which we'll talk about later on. V stable. In other words, nickel +2 makes a very stable ammonia complex. But nickel +2 does not make a stable material with carbon monoxide. So what's this tell us? Does nickel carbonyl, nickel tetracarbonyl, this stuff. Here's the $64 question. Does the stability of nickel tetracarbonyl appear to depend on the strength of the sigma coordinate covalent bond between nickel and carbon monoxide. Does the stability of nickel tetracarbonyl appear to depend on the strength of the sigma coordinate covalent bond between nickel and carbon monoxide, given that nickel +2 won't react with carbon monoxide, but nickel 0 does? because Coulomb's law demands that we realize this thing is going to attract non-bonding electron density from carbon monoxide. This is going to attract it more strongly than nickel zero. Yet this does not react with carbon monoxide, but nickel zero does. So I repeat the question. Does the stability of nickel tetracarbonyl appear to depend on the strength of this sigma coordinate covalent bond? Yes or no? You're going to scratch your noggin about this. What's the facts tell us? Answer this question, yes or no. There's the answer. No! If nickel plus 2 does not react with carbon monoxide, given that nickel plus 2 will attract this non-bonding electron density much more strongly than nickel zero, it follows that the stability of nickel tetracarbonyl cannot depend on sigma coordinate covalent bond strength between carbon monoxide and nickel. In fact, we've also verified that this sigma bond strength between nickel zero and carbon monoxide has got to be weak. Hell, remember this? Carbon monoxide doesn't even get in the game when it comes to H plus competition. Well then, what kind of bonds can we have at a covalent bond site which will stabilize the integrity of the material if they're not sigma bonds? Pi bonds! How about that? So we're going to write a statement here. Facts dictate that. And we've just been surveying the facts. Stability of this depends on pi bonds between nickel and carbon monoxide. Because we've now succeeded in ruling out the possibility of the stability of this depending upon sigma covalent bonds. So it must depend on pi covalent bonds. Now then, if nickel is to make pi covalent bonds, which orbitals will it use?
P. S.
Never.
No, couldn't be.
Here is the valence configuration for nickel. Got a full complement of 3d electrons after the bond interaction with carbon monoxide. Okay? We're recognized by that conversion of paramagnetic to diamagnetic character. Can I make pi bonds with 3d orbitals and 3d electrons? Can I make pi bonds with d orbitals? Yes or no?
Yes.
Of course. And the d orbitals that I'm considering are those which belong to nickel and which, after the bond interaction with carbon monoxide, full. Three d orbital. Nickel, full of electrons. If carbon monoxide is going to engage in pi bond formation, What orbitals must it use? Well, what valence orbitals do the component atoms of carbon monoxide possess? They're from period 2, aren't they? S and P is the only valence orbital period 2 atoms have. And you can't make pi bonds with S orbitals. So it's got to be P. There's nothing left. Now, admittedly, 2p orbital is going to be smaller than a 3d orbital, so I'll redraw the picture like this. There's a picture, an orbital overlap picture of a 3D orbital overlap with a 2p orbital to make a pi bond. There's our two regions of orbital overlap. Pi bond between 3D orb and 2p orb. Now we go back to carbon monoxide. Let's redraw the picture. And ask this question. How can CO pi bond? Where are these empty p orbitals? Because what we're focusing on now is a misstatement that's offered by Lewis structures. Consider O2. Did you learn in Chemistry 2045, or have you heard that a very important and significant property of diatomic oxygen is that it is paramagnetic? Have you heard that? I'm just curious. Did you hear this? Diatomic oxygen is paramagnetic. In 2045, did you at all look at molecular orbital considerations? I'm asking. If you didn't, that's okay. Yes or no?
Yes.
You did. And you didn't hear about this being paramagnetic? I'm just curious. Okay. Paramag. So, on your paper right now, I want you to play a game. I want you to write a Lewis structure for the diatomic oxygen molecule, which exhibits its paramagnetic character. Considerations along the way. Is diatomic oxygen an even electron species? How many total valence electrons? 12. All right. So you got to make a Lewis picture with 12 valence electrons, and which shows each oxygen atom in what kind of valence electron environment? What kind of valence electron environment for each O atom? Octet. Octet, right? So the picture you're going to draw has got to show each oxygen in an octet, and it's also got to exhibit the paramagnetic character of the molecule. Can you draw this Lewis picture? How many drew this? Well, if you didn't draw this, you drew something different. 2, 4, 6, 8, 10, 11, 12. 8. So there's my octets. for each oxygen atom and 2 unpaired electrons. Now then, Lewis structure people, do you accept this Lewis structure? If you don't accept it, tell me why you don't accept it.
Because you can't, I mean, that's how it is, but you can't, like, have 2 orbitals or just an orbital not filled.
What is that?
2 of its orbitals are filled, you could pair them up. Have it
2 of its orbitals are filled.
aren't filled.
Aren't filled.
Yeah.
Okay.
I got an idea.
Well, 2 of its orbitals can't be filled if it's paramagnetic.
Yeah.
Okay. So what's wrong with this Lewis picture?
It's like resonance, in a way,
No, it's not.
because
No, it's not. There's no resonance.
bonds go between both oxygens.
What is that?
The oxygens, each oxygen, the 2 electrons,
You're saying that?
they flip.
Flip.
Yeah, of course you're not going to accept that, but
I don't know what you mean by
they
flip.
exchange.
Well, I agree there's no way to tell which oxygen atom bears the 2 unpaired electrons.
Right.
So what?
So you can't.
I want to know, for those of you who've learned to write Lewis structures, which is every one of you, why you would not accept this Lewis structure. Because I'm wanting to point out to you a very important shortcoming of Lewis structures that at this point you need to learn about. Point. From a formal Lewis structure analysis standpoint, this picture is a violation of writing Lewis structures. Why? Because it says that this oxygen atom, which has a total of how many valence orbitals? Oxygens from period 2. How many valence orbitals does period 2 atom have? 4? 1 orbital filled, 1 orbital filled, 1 orbital filled, 1 orbital filled. That uses up all the valence orbitals for this oxygen. This oxygen atom. 1 orbital filled, another orbital filled, another orbital filled, another orbital half filled, another orbital half filled. That suggests for this oxygen atom how many valence orbitals? 5. But that's a lie. Because in a valence orbital, how many electrons max can you put? 2. So this really constitutes how many occupied valence orbitals? How many? How many electron pairs are you looking at here? So this really constitutes 2 orbitals, not 4. And that's one of the things wrong with Lewis pictures. Because what a Lewis picture shows you is the correct number of valence electrons. But it doesn't show you the correct number of valence orbitals. Each oxygen atom is from period 2. Each oxygen atom has 4 valence orbitals, which means an oxygen molecule has got 8 valence orbitals. Count them. 8 valence orbitals. So let's look again at this picture and see how many orbitals are really occupied. 1, 2, 3, 4, 5, 6, 7. There's another orbital there. And it's empty. It's not occupied. And Lewis pictures don't show you these empty orbitals. All they show you are occupied orbitals. Because all the Lewis picture shows you is valence electrons. It doesn't show you empty orbitals. So the point is, how can carbon monoxide make pi bonds? So we finish today with a directive. Here's your directive. See page 25(4). Examine MO diagram for carbon monoxide. What's MO mean? Molecular orbital. Do that. Pick it up from this point next time. And of course you're going to carry on with this stuff in tomorrow's discussion class, except that tomorrow I'll finish this stuff on Monday, what we're presently talking about, the tail end of chapter 23. So